Hello everyone, welcome back to the problem solving series. In today's video, we're going to be going through the forces from springs, also known as Hooke's law. So first I'll go ahead and run through the equation along with a couple of the key concepts for this force, and then we'll run through an example where you can see it in action and how it connects to everything we've learned up until this point. So the equation for Hooke's law, which I will pop over here, is going to be that the force of the spring is equal to negative k times delta x. So the negative sign here is a really important concept when it comes to spring forces. So that tells us that the spring force is a restorative force. And all that means is that the more and more that you stretch the spring, the more and more that the spring is going to want to go back to its equilibrium position. So the further you stretch it, the bigger the force that you'll have, but pointing in the opposite direction of the stretch or the compression. So that's where that negative sign comes in. It wants to put it back to where it was. That spring constant K is going to be inherent to whatever spring your system happens to be using. And otherwise, this force behaves just like all the other forces that we've seen up until this point. So you want to make sure that you're drawing it on your free body diagram. If you have a spring, then you should have an Fs on there. Break it into components if you need to, and then use F net equals ma to solve for what you're looking for. So let's jump into our example problem.
A mass is being held in the air by a spring and a rope. If the mass is 10 kilograms, the spring constant is 50 newton per meter and the tension is 25 newtons. How far does the spring stretch? Okay, so first thing I want to do is just go ahead and highlight some of the information within the problem. So they give us the mass, the spring constant, and the tension. And then let's go ahead and look at what forces we have. So we have a spring. So we'll have force spring pointing towards the spring since the stretch is going to be in the opposite direction, so it wants to unstretch. We're going to have Fg pointing down, and then we'll have tension pointing along the string. So before we can go ahead and use our vector addition of our forces, we need to break down that tension into a vertical component Ty and a horizontal component Tx. So using our SOHCAHTOA, we can say that Tx is going to be equal to T cosine 30 and Ty will be T sine 30. Now we can go ahead and set up our force equations. So sum of the forces in the y equals 0. And our vertical force, we have a positive tension y minus Fg equals 0. So because we're only interested in the stretch of the spring, we actually don't need to set up y forces, but it's always good practice just to go ahead and do that. But we're really interested in the sum of the x forces, which will also be equal to 0. And we'll have positive spring force minus Tx equals 0. We can substitute in that Fs is minus k delta x, and that Tx is T cosine 30. We can add the T cosine 30 to both sides. So we get negative k delta x is T cosine 30, and then we can divide out this negative k. And we'll plug in. So our T was 25 cosine 30 divided by negative 50. And this equals 0.433 negative 0.433 meters. So just to put into context again our negative sign, so this is going to tell us that the spring before unstretched looked like this, which means our delta x is pointing along the negative x direction in order to get that stretch. And there's your spring force.
Good boy! And say bye to the kiddos. Sit. No. Nuh-uh. Sit. Good boy. You ready?